All right, well, that gives you some idea of what the expectation is as far as the derivatives you should be able to handle. And the time that I gave you to do it is about what I would expect for a test. You know, that shouldn't take more than 15 minutes tops to do those problems. If that's going to take you more than 15 minutes, then you're not going to finish the test, because tests will have a lot more than that on it, you know? So you want to be working on not only understanding what you're doing, but the speed at which you're doing it, all right? So our next test is, what? It feels like it's coming soon, but October 11th. That's really coming soon, right? We have next week, 2 lectures next week, and then the following Tuesday is your exam 2 over chapter 2. All right. All right, so lots to do for you, I guess, over the weekend. All right, so we finished up. Notice I did not put implicit differentiation on the quiz. I don't know if that was good or bad, but you studied more implicit differentiation. The reason why is because I gave that exact identical quiz to my Monday, Wednesday class, which that's the first time this semester I gave you all the same quiz. And they had not seen implicit differentiation, so I didn't obviously put it on there, so I just gave you the same thing. All right, I said today we're going to do more implicit differentiation, and then we are going to just get a glimpse into 2.7. 2.7 is going to take us part of today and all of next week we're going to spend on 2.7. Find the equation of the tangent line to this curve at this point. And this is right out of the book. It's called a cardioid. And here's what it looks like. And we're trying to find the slope of that tangent line at that point, 0, 1/2. Understand? So what we need to know in order to find the equation, sorry, I said the slope. The equation of tangent line, remember, it goes back to this. Y minus y1 equals m times x minus x1, right? That's the equation of any line. The line that we're looking for is a tangent line. So this this slope is actually the derivative, right, at the point we're talking about. So this is, you could say, this is the derivative of the function at the point, right? That's what that has been in the past. I mean, that's what it's been in the past, right? It's the derivative of the function at the point. Problem is, this isn't a function, right? Fails the vertical line test. So we're going to kind of scrap that. We want dy dx at that point. Now we can find dy dx. That's what we spent last class doing, right? Yes? Y'all look stunned. Are y'all okay? It's just a quiz. Big deal. It's over, right? Everyone's all right? Where's my... There it is. So what am I going to do here to find dy dx? What type of differentiation am I going to use? The standard one or the implicit one? Implicit, right? Because you can't solve that for y. It's not going to happen. So I'm going to take the derivative on both sides with respect to x, right? So let's see how you do with this. What is the derivative of the left side? So what are you going to do?
2x.
Separately, right?
Yes.
So derivative of x squared with respect to x, just 2x, right? Plus, now this is the one you have to be careful with. What's the derivative of y squared with respect to x?
dy dx 2y.
2y times dy dx. Left side's done, right? Okay, on the right side of the equation, what do you see? Chain rule. Hopefully you all see you've got a big clump of junk squared. What is the derivative of a big clump of junk squared? 2 junk to the first power, right? Understand that? To the junk to the first power, which I don't need to put. So I'm doing chain rule, right? Times, now I go inside, I look at the junk, here's all the junk, and I try and take the derivative of this with respect to x. There's 3 separate terms, so I can do them one at a time. The first one has just x in it, so it's going to be a standard derivative. Derivative of 2x squared is 4x. And I'm going to put a set of parentheses here because I'm going to have more than one term, right? So 4x. And then the derivative of 2y squared. This one's tricky, I guess. 4y dy dx. Plus 4y dy dx. That's some chain rule on that. And then minus 1. Close the parentheses. Are we done? Yeah, we're done because the 2 came out. 2 times the junk to the first power times derivative of what was inside. We have exhausted the function. We've done everything, or the expression. It's completely differentiated. And I'm trying to find the derivative dy dx at a specific point. Do you see dy dx in here? Yes, that's good. Now in the previous class, what we did at this point is we solved for dy dx, didn't we? We isolated it on one side. But in this problem, because we're looking for the dy dx at a specific point, we can just go start replacing x and y with 0 and 1/2 now. And it'll make it cleaner before we start moving things around. So everywhere I see an x, I'm going to put a 0. Everywhere I see a y, I'm going to put a 1/2. Do you understand what I'm doing? Okay. So at the point 0, 1/2, this equation becomes 2 times 0, don't need to write that, plus 2 times 1/2 dy dx, that'll be a 1, equals 2 times 0 squared plus 2 times 1/2 squared minus 0 times 4 times 0 plus 4 times 1/2 times dy dx minus 1. I think I got that right. Looks like all my x's are zeros and all my y's are half.
So when you're going through doing this, you just leave dy dx?
Yes, because that's what we're going to solve for, right? This is an equation. The only variable left is dy dx.
Okay.
So this is gone. Half of 2 is 1, so just dy dx there. Equals, let's see, that's gone.
It's going to be 1.
This is going to be 1/4, right? You square that first. 1/4, 2 times a fourth is a half. And then times 2, so that's going to be a 1. And then times, let's see, that's gone 0. 2, right? 2 times dy dx. So 2 dy dx. And then minus 1. Right? So I didn't need that 1 out front, right? But just to show you what's happening.
The heck, why is dy dx? Or
It's not, there's 2 of them.
never mind.
Yeah, there's 2, so when we move it, it should be okay. So we get here, oh, no equals, sorry. We get dy dx equals 2 dy dx minus 1. So I guess what I'll do, this is really up to you which side you move it to. I could move it over here, right? Subtract 2 of them on both sides. Or I can move this one over and subtract 1 of them on both sides and then move the negative 1 to the other side. Either way, this is kind of just algebra at this point, right? Moving things around. So,
dy dx
should be dy dx equals 1. Right?
Yeah. 0 and negative 1/2. That's the slope.
This is just the slope of the tangent line. Now let's go write the equation. You ready for the equation? This is just the slope. So the equation, I want to leave that there, was y minus y1 equals m times x minus x1. So y minus, because I'm at the point 0, 1/2, y1 is a half, equals m, which is 1, times x minus 0. And you can distribute the 1 through and bring the negative 1/2 to the other side, and you should get, as a final answer, y equals 1x plus a half. So if you graph that line, it's that one right there. It has a slope of 1, and it passes through that point 0, 1/2. It's tangent to the curve. We good? All right, let's do another one. Same instructions. This time I'm going to give you a few minutes to work on just getting the derivative. I want everyone to try and get the derivative, all right? You don't need to go through and do all this yet, all right? In fact, I'm just going to give you the function. I'm not going to tell you the point yet. That way I'm forcing you to stop. Okay, y squared, and then times y squared minus 4 equals x squared times x squared minus 5. This is in the homework, but this is a different, I don't think I assigned this number. But it's in the exercises. This is actually called Devil's Curve. That's the name of this. The graph is, I don't know where the devil's curve is coming from. I guess it kind of looks like a devil. It looks like a figure 8, like this, and then it does something like this. Like that. Devil's curve. All right, get the derivative. Try it on your own. Give you a few minutes, maybe like 3.
This would be the raw derivative, right?
You're differentiating implicitly, so just derivative both sides, right? With respect to x. And then we'll talk after a couple of minutes. See people like looking at me. Does that mean y'all are done? Yeah, kind of, you think? I'm going to give 1 more minute till 1:37. Okay. How many of you looked at this and said you're going to need to do a product rule right here? Anybody? Yes? And a product rule here. Okay. How many of you just distributed y squared through and x squared through? That's the cleaner, easier way to do this. So this goes back to the whole idea of you have to kind of like look at what you have and think about what you can do. You don't want to be robotic and be like, you know, I see product rule, I do product rule. You know, like you want to think, I can distribute that. There's no problem with distributing that, right? If I distribute that, I'm going to get y to the fourth minus 4y squared. If I distribute the x squared through, I'm going to get x to the fourth minus 5x squared. Okay, so that's easier to differentiate because I can just do it term by term, right? No product rule at all. Do you see how much cleaner that's going to be? Now, could you have done it with the product rule? Yes, you could have. And maybe I'll write down what that would be, but let me do it this way first. So I'm going to take derivative of this with respect to x, which will be what? 4y cubed. What's that? dy dx minus 8y dy dx again. Okay, good. That's your chain rule happening. Minus 8y dy dx. And then how about on the right side? Just your standard differentiation, right? That's it. Because you're differentiating with respect to x, right? Questions? Now, I didn't give you a point. Now, oh, you want to see it with the product rule? Just to see if you would have had it right? Because I know a lot of you did do the product rule.
Sure.
All right, if you would have done the product rule, you should have had 2y dy dx times y squared minus 4 plus 2y dy dx times y squared equals 2x times x squared minus 5 plus 2x times x squared. That's what it would have been had you done the product rule. So it's doable. It's just a little uglier. Now let's find the equation of the tangent line at this point. 0, negative 2. I'm going to use this one. I think it's a little easier to plug in here. So I'm going to plug in 0 for x and negative 2 for y. So if I plug in 0 right here for x, it's gone. That's great. Everything's gone over there. And negative 2 for y. So I do negative 2 cubed is negative 8 times 4 is negative 32. If I plug in negative 2 right here, I'm going to get negative 8 times negative 2 is positive 16. So 16 dy dx. And it's really, pardon?
It's going to be negative 16 dy dx.
Oh, okay. When you put them together, negative 16 dy dx equals 0, and then divide both sides by negative 16, and you still get 0. Which means you should have a horizontal tangent line, right? The slope of your tangent line is 0. So what's the equation of that line then? If you draw the picture, yeah, it goes like this, right? And the equation of a horizontal line is y equals a number. That's the equation of a horizontal line. And we just need to know what the y value is for that line. And what is the y value of that line? Negative 2, right? Negative 2. So y is negative 2. Now you could have used the formula y minus y1 equals slope m, which is 0, x minus 0. And if you just do this, and you'll get y is 2. Y is negative 2. You just move that over to the other side. That make sense? Questions? Comments or concerns? Complaints? No. Like I've said, I'm just the messenger, okay? This is calculus. So let's just change it up a little bit, something a little different. How about if we have x to the fourth plus y to the fourth equals 8, let's say. Yeah, okay, we'll go with 8. You know what? I want it to be a nicer number. I was going to go with 64, actually. I was going to change it a little bit. Here's what I would like us to find. Find y double prime. Remember first derivative, second derivative? We need to find the derivative 2 times. Now please understand, in Leibniz notation, what this means is I want dy dx, right? Not squared, right? Not squared. But I want to take the derivative again. So Leibniz did this thing where it was like that thing, remember? Like offset the numbers so that you know the second derivative. But for this problem, I'm going to stick with the prime notation because I want you to see that you can maintain the prime notation as long as you all understand and agree that what we mean by y prime is dy dx. Okay? So please understand that's what I mean by y prime. I am letting you know I'm differentiating with respect to x. All right, so let's do implicit differentiation. What's the derivative of x to the fourth with respect to x? 4x to the third. What is the derivative of y to the fourth with respect to x? 4y to the third, dy dx, right? But I'm going now to write y prime instead of dy dx. Now, I'm only showing this to you because the book shows it, and in other classes, in other calculus classes, they may stick to that notation, all right? So can we still do this without getting ourselves into trouble? Equals 64 derivative, right, which is 0. Okay. At this point, I'm just going to notice a couple of things. Like first, there's a 4 and a 4, right? So I could divide everything by 4. If I divide everything by 4, it's going to look a little nicer. Like that, right? So I started with an equation that had no derivatives in it. I differentiated implicitly and created an equation that now has the first derivative in it. I'm looking for the second derivative, which means I'm going to need to differentiate again to produce a second derivative. Do you agree? So let's differentiate this equation again with respect to x. What's the derivative of this with respect to x? 3x squared. Plus, now, what to do here? What to do? Will it? Yeah, what do you think? Is that what you're thinking? Just derivative of each one?
I mean, because you'd have 3y squared times
What?
y prime times y prime.
Back up. You're telling me this is y cubed times y prime? That's a product, is it not?
Yeah.
And if I'm taking derivative of a product, I have to apply the product rule. So life would be nice if we could just do derivative of each one, right? But it's a product, we got to go product rule. We have no choice.
This would have been nice. I went the other way.
But it's doable. Like we're still following the same procedures that we had before. What is the derivative? We're going to do product, right? Derivative of the first one times the second plus derivative of the second one times the first one, yeah? What is the derivative of the first one? What's the derivative of y cubed with respect to x? 3y squared times dy dx, or y prime, right? That's what we did last class. But then, that's just derivative of that, right? Times what? Y prime. Times y prime. That is not y double prime. That is y prime squared, right? That's not what we're looking for, but I've got y prime times y prime. Do you see that? Pardon?
Give me d2y dx squared.
I don't know if I heard you. This right here is dy dx squared. All of it, the whole thing. But it's not what we're looking for, right, which is the second derivative. But we're not done yet with the product rule, are we? That was the derivative of the first one times the second. Now we do what? Plus the derivative of the second one. I'm taking the derivative of the derivative. What's the derivative of the derivative? The second derivative. That's your second derivative. You see, it comes, your second derivative that we're hoping to solve for appeared right here when we did the product rule, when we were doing the derivative of the second one times the first. Derivative of the second one was the second derivative. Yes?
Okay, so on back on the y, the first like y, yeah, right there.
Uh-huh.
Okay, the reason you had to add another dy dx because you did the derivative of the y.
Of y cubed,
Yeah, okay.
right? Yes, the derivative of y cubed
Then you added
with respect to x is 3y squared times y prime, or times
the second derivative is, yeah.
derivative of this one. I'm not done. I still have to tack something onto that. Yes?
Could you just put y prime on one side first? And the rest
Okay, so another method would have been to solve this for y prime, and then the derivative of the left side would have been y double prime. And then the right side you would have had, well, in this case you would have had quotient rule on that side, because that's just the way it would have worked. Yeah, you can do that, yes. Uh-huh, yep.
I think I like that method better than this one.
Well, either way, you have to, you have to do it. So, I'm not done with product rule, right? What am I still missing? Times y cubed.
You don't have another try?
No. No,
Even though we're starting to respect the x.
that's right. Yep, because it's not chain rule. When we're taking derivative of y prime, we're not saying like the 1 comes out or anything, or like we're just saying what's the derivative of the derivative? It's the second derivative. You don't then go inside and take derivative of the base because we're not using the power, so we don't have to go inside. That make sense? Okay. So there was there was the y cubed that we had to tack onto the end. And then equals 0 still, right? Equals 0. All right. Yeah. Let's isolate y double prime. So I'm going to write this as 3x squared plus 3y squared times y prime squared plus y double prime times y cubed equals 0. The only thing I did there is I put the y primes together and put squared. And I'm going to move both of these terms to the other side. All right? So I'm going to have y double prime times y cubed equals negative 3x squared minus 3y squared times y prime squared. And then what am I going to do? Divide by y cubed. Divide both sides by y cubed. So when I divide this side by y cubed and divide this side by y cubed, I have an equation that has y double prime, right? Are y'all good with that? I'm not done, but are you okay with this up to this point? Yes.
One more time where that second y prime came from.
Man, I'm trying to think of another way to explain it. Look, if I just walked in here today and I asked everyone what's the derivative of y cubed, what would you tell me? From last class, you would tell me it would be 3y squared times dy dx, right? That's what you would tell me. 3y squared times dy dx, which is the same as me saying 3y squared times y prime, right? Yes? Okay, so when we were here and I did product rule, it was the derivative of the first one, which is that, right? Then what? Product rule says derivative of the first one times the second one. There's the second one. Derivative of the first one is this, times the second one, plus the derivative of the second one times the first. right, where am I going to write this? I guess I'll write it up here. So here's what we've got. Y double prime equals negative 3x squared minus 3y squared y cubed. I realize that I have that there, okay? But I think I know a little bit of information about y prime, don't I? If I come back over here, because look, at this point in time, for me to tell anybody, let me write it up here for now. For me to tell you any information about the second derivative, you must be able to provide for me not only the x and the y coordinate, but you also must provide me the derivative, the first derivative, information about the first derivative. I would prefer if we could just write this so that it was all in terms of just x and y. You just give me the point and then I can tell you what the second derivative is. This requires the point and a derivative. So yeah, what we're going to do is we're going to go back to this equation and we're going to solve it for y prime. And whatever that is, we're going to stick it in there. So come back in here. You know what? We got rid of the 4's, didn't we? Okay, so take that one right there, solve for y prime.
Negative x cubed.
Y cubed times y prime equals negative x cubed, right? Move that to the other side. Divide both sides by y cubed. So y prime equals negative x cubed over y cubed. And I'm going to put that right there. I'm going to rewrite it. Y double prime equals negative 3x squared minus 3y squared times, bless you, negative x cubed over y cubed squared over y cubed. And if I take a fraction, bless you, and square it like I'm going to, I can square the top and bottom separately. And if you take negative x cubed and square it, that's negative x cubed times negative x cubed, which is positive x to the 6th. This will be y to the 6th. So that's my next line. I might need that, what I just erased. Oh well. So here's where I am. Y double prime equals negative 3x squared minus 3y squared times, we just said it was going to be x to the 6th over y to the 6th all over y cubed. Yeah? I can do a little more cleaning up, can't I? Like this right here is really like a what? Y to the 4th on the bottom. Equals negative 3x squared minus 3y squared. Oh no, sorry, that y squared's not there. It's what? 3x to the 6th over y to the 4th all over y to the 3rd. I'm going to try and do a little bit more, just a little bit. Maybe a common denominator on top? Or y'all don't like that? Y'all are happy like this, right? It's just like there's x, there's y. But I have this like really, really bad feeling that we can do some more simplification. Like, I don't know. Slightly. I adjusted it a little bit, but let's just keep working. Okay, let's keep working. Let me do this. See if you follow me. 3x squared y to the 4th minus 3x to the 6th over y to the 4th. Okay, I'll do that. Over what? Y to the 3rd, but that could be looked at as y to the 3rd over 1. And then I could flip that like this. And so really I could have just written what down here? Y to the 7th. right? So I got a common denominator. I got a common denominator between these two, put them together. And then when I do this and flip, this can become 1 over y cubed like that, multiplication. This will be gone, and I put those together, y to the 7th. Okay, let me do that. It's starting to look nicer and nicer. Negative 3x squared y to the 4th minus 3x to the 6th over y to the 7th. Anybody recognize like a GCF on top? Negative 3x squared. Do y'all see negative 3x squared on top? This is about to be holy shit right now. I need to stop cussing on video. I really need to stop doing it. It's very unprofessional. I've come to the conclusion I'm never going to stop. Okay, what happens when I factor that out? What am I left with? What is it? Y to the 4th plus what? The 3 came out though. Negative 3 came out.
X to the 4th.
No, the 3 came out.
Or
X to the 4th? Anyone see it? What is x to the 4th plus y to the 4th? 64. Right? I mean, look, this to be on this curve, right? To be on this curve, this equation must be satisfied. All the work that we're doing is based upon that equation. So if in our answer we see that equation, we know that it must be this. So I can replace this with 64. So what would be, if this is 64, then what's negative 3 times 64? Negative 192? Negative 192 x squared over y to the 7th. Now that is clean. Right? What other way?
You just take a derivative twice.
You mean solve for y prime then derivative? Are you asking me can we do that, or are you asking me to do that?
Both, I guess, technically.
Yeah, you want to see the other way? We can do it the other way, just to do it. But do you all understand what we did here? There are a couple of problems in the homework, numbers 25, 26, and 27, that are like this. And I think I did some of them on video, maybe not all of them. And on the one that was the hardest, they were knocking on the door for me to get out of the room, and I was like rushing through it. So I don't know if you're going to follow me through it all, but these are good problems as far as the algebra in here, right? There's a lot of algebra to get a nice, clean answer at the end. All right, so you want me to do this problem, the same problem, right? But you want me to do it slightly different, which I'm open to. So do you agree we had gotten down to this? No, that's not what we had.
You had y
Is it?
prime equals negative x.
Well,
It was just the negative x squared over y cubed.
yeah, but okay, so when we had done our work, we had gotten to this, and then we took the derivative again, didn't we? We just went straight from here to get the second derivative. We did implicit again. But you could have, instead, solved this for y prime now, okay? So if I solve this for y prime now, we get negative x cubed over y cubed, right? And now, let's do implicit differentiation on this instead of that. That's what you're suggesting we do, or whatever his name was suggested we do also. And I said, yes, you can do that. What is the derivative of the left side? What's derivative of a derivative? The second derivative. So the left side is your y double prime. Look, check that out. It's already there. Solve for it. Isn't that beautiful? Okay, what about the right side? Quotient rule. Derivative of the top times the bottom minus derivative of the bottom times the top all over the bottom squared, right? So what is the derivative of the top? Negative 3x squared, right? Times the bottom. minus the derivative of the bottom, 3y squared dy dx, which I'm going to say is y prime. So there's your chain rule on the 3y squared part, or the y cubed part, times the top, which is negative x squared. Right? The top was, why did I say x squared? I said x squared, I meant what? Negative x cubed. So it's negative x cubed being multiplied right here, but I changed the minus to a plus. All over y cubed squared. Okay. There you go. So now at this point, you would have to go in and replace y prime with this.
That's so much nicer.
Perhaps. The reason why I didn't show this to you isn't because I'm like, I'm going to show them the hardest way because I enjoy torture. It's because you can't always solve this for y prime. Sometimes this y prime is trapped somewhere and you can't get it solved by itself, or sometimes you have two of them. So we should just be ready if we need to just take the derivative again. And well, then you go drop the class, I guess. That's what I would do. That's torture. You know, that's just torture. The third derivative on something like this would just be trying to make a point that at some point everyone will surrender to the problem, right? Yes? Because it was derivative of the bottom times the top. What was the top? Negative x cubed, but this was a minus, so I just, instead of putting negative x cubed here, I just changed that to a plus. Do I need to go on, or this is okay? So you see you put it in there, and then hopefully it would simplify and...
We just leave it like that.
No, you want to get it to look exactly the same as my answer was.
Can you simplify before putting in y prime?
Simplify what?
I guess like take out the 3y squared top and stuff.
Before this? Yeah, you could factor out like a y squared, and you could reduce it and cancel. Yeah, you could do all that. You could have even done this. At this stage up here, you could have looked at this as being negative x over y cubed and done chain rule, and this would have turned into 3x, negative x over y to the second times, now I could do quotient rule on that, which would have been negative 1 times y minus y prime times negative x again, which would have changed it to a plus over y squared. That's nice too. You could have, I mean, look, there's a lot of different paths we could have gone. I could have looked at this and rewrote it like this. Negative x to the third, y to the negative 3, right? Brought the y up, and then I could have done product rule on that. I mean, here's the good news when it comes to math, is that we should all get the same answer, all right? It's not like, well, I did it this way, so mine's going to look, mine's a different answer than yours. No. I mean, that's part of the beauty of it, is that we should get the same result, right? As long as you don't break any rules, there's consistency, always. It's not open to interpretation. At least not here. Later on, I guess, it does kind of get gray. Some gray areas in it, but... All right, well, I think that's it. I think I'm ready to put this one to sleep. Implicit differentiation. The main ideas on implicit differentiation are that we can differentiate any equation with respect to any variable, right? Any equation with respect to any variable, that we just have to maintain the product rule, quotient rule, chain rule, power rule, just maintain the rules, and we're in business.
Does 2.7 add on to what we just learned?
It incorporates what we learned, so it's going to use, we're going to need implicit differentiation to solve the problems.
Okay.
Now, I want you for the weekend to watch the video for 2.7. It's going to be a lot of me talking and you watching animations that I've created for 2.7. I think it's kind of long. And we're going to come in and we're going to talk about each of the problems that I show you animations for in the video. We're going to come in and solve. But today I wanted to kind of motivate the idea of what this whole section on related rates is about. And I've never presented it the way I'm going to present it right now today. So this is kind of you're my guinea pig class. I thought maybe it might make sense this way. We'll see. As just a motivating idea. So I threw some code together before class, and I have a picture. Now, I had to zoom in on it on purpose. I'll tell you why in a minute. This is just the equation y equals x squared. I mean, this is our classic parabola, right? There's no craziness to this. If I ask you for y prime, which is the change in y with respect to x, then everyone here should tell me 2x and be done with it, right? And what this 2x represents is if I go to a value of any value, right, I want on the x-axis, let's say we go to 4. I know this is really hard to see. This says 2, 4, 6, 8, 10. And then up here this is 20, 40, 60, 80, 100. If I go to 4 and go up to the graph on 4, where would I be at? 16? Right, 4 squared, I'd be at 16. And what does this give me? Slope. So what's the slope at that point? I'm at the point 416, right, on the graph. What is the slope of the tangent line here? 8. Okay, I thought I heard 18. 8, right, that's what this function gives us. If I plug in this x value right here, I get 8. And that should be the slope of this line. So if I draw the tangent line, the slope of that thing should be 8. Got it? I mean, this is what we've done. That's not what today is about, though, all right? What this section is about. This has to do something with kind of a totally different concept, still using the same graph, y equals x squared. I want you to imagine that I'm going to come in here and draw this with my hand, all right? Just with my pen, we're going to start drawing you y equals x squared. I'm going to start at 0, and I'm only going to draw the right side of it. Okay? So as I draw this, imagine that for every point I have to move to the right and up, right, to draw each point. So as I draw the curve, if I'm drawing a curve, I'm moving right while I'm simultaneously going up. So it's hard to get a computer to do that, right? It took us a long time to get even a computer to do something like that. So our brains are pretty advanced that we can draw a curve because we have to do two things simultaneously, right? Now, if I draw a straight line, it's the same concept. I'm going over while I'm going up. But it's different than this because when I draw a parabola, the rate at which I go over is not the same as the rate at which I go up. Understand? With the straight line diagonal, the rate I go over is the same as the rate I go up, right? Because it has a slope 1. So, with that kind of concept in mind, I'm going to start drawing this curve, and what I'm going to tell you is this. In the x direction, I'm always going to be moving at the same speed. Okay, so imagine as I'm drawing to the right, I'm also moving up, right? But let's just focus on me going to the right. I'm telling you that as I draw this, let me do it this way. As I draw the point, and if you watch what's happening in the x direction, as I move up the graph, this direction is always moving the same speed. Is the y going to be moving the same speed? No. So I tried to make this animation make sense. I'm going to go back to the beginning. And what I want you to pay attention to is the x value, just the x value. I just want you to watch it. Let's try this. This might be too slow, but let's just notice, don't even look at the y, just the x. That's too slow. Let's watch the x. So we're going to count it. 1, 2. I still think that's too slow. Sorry. This should count. It should be 1 second. So this should be 1, 2, 3, 4, 5, 6. So do you see that the x is counting like 1 second? Every second I move 1 unit over. Make sense? So the x keeps growing by the same amount. It's constant. But look at the y now. Notice in the y direction, look at how fast it starts to grow. Do you see how the rate at which it's increasing is getting faster and faster and faster? Yes? So the question that we want to ask is this. If you stop somewhere, if I stop right there, and I'm drawing it, and I'm telling you that my x direction is a constant, at that point that I stopped, I want you to tell me how fast the y direction was. Not what the value was, but how fast it was moving up. Does that make sense at all to you? These are called related rates, because what we have is an equation that relates two variables. Right? Here's the equation that is relating the two variables together. Then we have the rate at which one of them is moving. One of them, I told you, was moving to the right at a constant rate. Yes? How is that related to the rate at which the other variable is moving? So what's the connection between what's the relationship between the speeds at which these variables interact with each other? Kind of. If this were a perfect diagonal line, pardon?
Seconds?
Yes, like in seconds. Yeah. If this were a perfect diagonal line, would you agree that the rate at which I change in x should be the same as the rate as I change in y? And that's exactly what it would be. All right? I guess I could change the code real quick to show that, but I guess we'll just leave it. So even though the x moves the same rate, the y is changing at a different rate. So here's I'm going to put the question up on the board and we're going to see if we can solve it. If y equals x squared, and I tell you that the rate at which x changes with respect to time. So I'm telling you that the x direction of the point is moving at a constant rate. The rate is a speed, speed is a derivative. So I'm telling you the derivative, the change, is 1, and I don't have a unit of measurement here, so let's just use feet. 1 foot per second. So I'm drawing this parabola. I'm drawing this parabola in a way that as I draw it, if you just focused on my direction of the x, that as I draw it, the x is growing at a constant rate of 1 foot per second. Understand? So if that's true and that's true, find the rate at which the y is changing. So what am I asking you for? dy dt at a specific point on the curve. So let me pick a point. How about that point 416? So I'm drawing this so that the x value changes at 1 foot per second. Exactly when I get to the point 416, how fast was that point moving straight up?
Do you need the y in that?
Do I need the what?
The y. Didn't you just say dy dt at 1?
At x is 4? In general, in 2.7, we'll need everything. But because we're starting with such a simple function, that we don't even need implicit differentiation for this function, because it's already solved for y, but we will use the whole point. Let's actually take the derivative, all right? Because look, what I want to know, right? I'm going to circle this. This is what I want to know, right? I want to know something about dy dt. The only things I know for sure are dx dt, and this equation must be true, and then that's a point on the curve. So how do you think I'm going to create dy dt from what I have? Implicit differentiation. I'm going to take the derivative of this, but with respect to time, right? I'm going to do it with respect to time. Not with respect to x, not with respect to y, with respect to time. we did talk about this last class, right? That you could differentiate with respect to something other than x or y. We're doing it now. So I'm going to take my derivative. I'm going to go a little slower, kind of like we did last class. I'm going to take the derivative of the left side with respect to time equals the derivative of the right side with respect to time. Both the left and right hand sides have variables that are not the variable I'm differentiating with respect to, which means both of them get chain ruled, right? Neither one of them turns into a 1. So what is the derivative of y with respect to t? dy dt. Am I happy to see this?
Yes.
Absolutely, because that's what I want. And then what's the derivative of x squared with respect to t?
2x dx dt.
2x dx dt. And we're there. We're there. We're pretty much done. Because what this equation tells me is that if I want to know the rate at which y is changing with respect to time, I need to know just two things. I need someone to provide me just the x-coordinate, right? Just give me the x-coordinate of where you are, and also give me the rate at which x is changing. And I have both of these, don't I? So what is, well, I should do it over here. So at the point 416, dy dt will be equal to 2 times 4 times what? 1. Which is 8 feet per second. Do you all remember last class where I started the class and I said, hey, this dy dx, that we've always assumed that dx was like unit time. Do you remember me saying it? Like a unit measurement? Does that ring a bell? Like a unit? I'm afraid I shouldn't say this, but the reason we got 8 as our answer, and that matches, doesn't that match the slope of the tangent line there? Is because my dx dt was a 1. What if my dx dt is something different? The answer is not going to be 8, is it? So if I start drawing this thing, if I move at a rate of 1 foot per second, then this answer matches the slope of the tangent line. But if I move faster in this direction, then that slope of the tangent line no longer corresponds with how fast the y is increasing. That might be a little too much for you to take, so don't worry about it. I would like to know what unit this answer is. Feet per second. Now, why is it feet per second? What's that?
Did you put it over there?
Well, that's what dx dt was.
Because there's no other unit.
Yeah, the units we're measuring here are in feet, right? And the time is in seconds. Yes? So what I'm going to ask you to do in 2.7 is to focus on your answer here. When you look at this, you look at this variable y. How is y measured? Well, we're assuming x is measured in feet because of the units I gave you. And that means y is in feet. And so this unit up here would be feet over, because this is a fraction, and then now you look at the time unit. And the time unit in the problem was seconds, right? We weren't talking about minutes or hours or days. So your answer would be feet per second. So if I'm moving across here, I'm drawing this parabola so that my x is moving at 1 foot per second. How fast would the y be increasing at x is 10? So if I get out here to 10, right, how fast is the y going up? It would just be this, right? This is our answer. 10 there, 20, and then dx dt in here is 1, so it'd be 20. 20 feet per second straight up.